This is Selwyn Williams. He's a senior R&D Group Leader with Sherwin Williams Protective and Marine Division. He oversees the design, development, and commercialization of coatings and linings in the global energy segment. He joined Sherwin Williams in 2002, held various positions in the Coatings Research and Development Group, and has been in the coatings industry for 25 years. So he'll talk about CUI.
Thank you. Thank you all for joining the talk this morning, and thank the Texas Chamber of Commerce for inviting us to present technology that we are currently working on that's near commercialization. So I just wanted to talk about how we change the landscape of thermal insulation coating with a focus on not necessarily CUI mitigation, as happens today, but CUI elimination eventually. So the team here that works on this, working on this project is myself, Jeremy Dahm, and Eric Brower. They're pretty heavily involved in this development. So outline for my talk today, we look at current insulative systems, concerns we have with CUI as pertains to current systems, thermal insulation efficiency, and application limitations with the current CUI systems that are in use today. Next, we'll have a brief discussion on the next generation of acrylic coatings for thermal insulation coatings, the product development that's ongoing in that technology, as well as some application challenges that we have and we have overcome in developing the application process for this technology, and in conclusions and some next steps that we are currently working through. Now, the idea behind this development was to challenge ourselves. How do we do better at corrosion under insulation, the concerns that are there, and how do we not necessarily, as I mentioned earlier, mitigate CUI, but eliminate CUI. So that's the challenge that we give ourselves, and talking to several in the industry, that's the way we want to go about this, to eliminate CUI. So you're all probably aware of some of the challenges that are present with CUI. Water is our enemy. So water and oxygen are the two main players that causes CUI. And it's worse when it comes to insulation, insulated vessels and so on. And temperature plays a big role as well. In addition, when you have covered insulation, you could have high concentrations of acids, salts, chlorides, and sulfates are big enemies there. If it becomes acidified, it's even worse. So here we state there is a cost of CUI issues. Industry spends about $2.6 billion. It's amongst about 10% of our maintenance budget. And per plant, that cost works out to, and this is mainly just speaking about ONG plants. The cost is about $1.6 million per plant per year. That's a pretty heavy burden, pretty heavy lift. CUI, it's the normal systems that we use today for CUI are mineral wool, calcium silicate, and some man-made mineral wool that are used. But they all have the same concerns. They all are installed the same way. You have a product stored in a tank or a product transported in a pipeline, and there's a lining in the interior of that product, of that substrate. The exterior is coated with a CUI coating. Between the coating and the cladding, you have a CUI, you have an insulation product, mineral wool or calcium silicate. And you typically would have accelerated corrosion if this material gets wet, and it does get wet. There's no way you can actually remove that water completely. Now, industry believes that you install mineral wool, it's normally rated at its dry, as a dry material, but it's never dry. It's always wet. Water gets in through various means. It's either through leaks in the cladding, or there are areas where the you can't have a complete seal. Water gets in there. Water gets in through the drains where you put where you have for the water that gets in to get out. So these are some examples of advanced CUI issues, and a lot of it comes down to the equipment design. That is hard to form insulation material and then clad it around some of the design that you will have in the in plant design or whatever. Here is a very small hole in this cladding, but it causes a lot of damage. And this is publicly available information from Mascote, who is one of the leaders in who is very involved in CUI mitigation using certain types of coatings. Now, when you install cladding onto a vessel or pipeline, there's various ways you would do inspections. Inspection ports, there's always the need to take it off to do a full inspection. That's the best thing you can do, is to remove it, but it's destructive and it's very expensive to do that. There's some non-destructive testing that you can do. List a few here, but these are all expensive. In addition to being expensive, some of these are also unsafe because they involve radiation. For example, the computed radiography and the neutron backscatter all involved radiation, so they're not necessarily safe. But these are the methods that are used today to do an inspection, non-destructive inspection on for CUI, and to ensure that the metal is not corroding under the cladding. Now, thermal efficiency. It is thought that when mineral wool is installed, it has a very low thermal conductivity, and it does. It's rated at 0.04, 0.05 watts per meter Kelvin, but that's dry, and it's never dry. So we measured moisture at one of the inspection ports with one of our development partners. So we partnered with companies to develop this technology, and allowed us to measure moisture in mineral wool on one of their tanks. And if you notice, it's measuring 5% moisture. Also, as mineral wool gets wet, the thermal conductivity of that mineral wool goes up. For good insulation, you want to have low thermal conductivity. So low thermal conductivity equals good thermal efficiency, and vice versa. High thermal conductivity equals low thermal efficiency. And this graph illustrates that. So you look at 4% volume of water in insulation, your thermal efficiency loses 71% of the thermal efficiency. So again, water is your enemy for thermal efficiency and also for CUI. Practical example. Again, we did have some collaboration with one of our industry partners, and you're allowed to measure water content across a conical tank roof at one of their facilities, and the measurement tells us that there's a lot of water in that roof. They were about to replace this roof, and they allowed us to go on site and pull samples. We sent the samples to our third-party lab, and these are the results that came back. So the tank is sloping outwards. So we had at position 1, we have 34% water by weight in that sample of insulation that we took, down to 69% water at the lowest point. So again, water is your enemy. Now, there are some limits, as I mentioned earlier, with installing conventional insulation, and it's mainly related to the design. You can't get around it because you have to form these metal structures around very unforgiving bends, unforgiving protrusions in the tank, pipes. You also have to work around areas where you have fireproofing as well, and it becomes a challenge. So I'm not saying that the TIC is the magic elixir to solve all the problems with CUI, but because there are limitations, and the limitations are currently there's some fourth generation products in the field, but it could only be applied between 20 and 50 mils per coat. So you apply several coats to get to a certain thickness to give you the thermal efficiency you want. And there's there's time the coating has to sit for a period of time before you can put a second coat on. So there's a lot of downtime between first, second, third, up to probably 8 coats of coating you have to put on to get to the same thermal efficiency as I would say mineral wool containing 5% water. There's also temperature limitations. These are polymeric materials, waterborne acrylics and epoxy syntactic material gets up to 35 for acrylics and 40 degrees temp resistance for epoxy. So there's limitations there in which you can apply the material. Some plants operate at temperatures higher than that. Some vessels and piping run temperatures 500 degrees F. And so there's limitations where you would have to use material besides acrylic coating that we have to have thermal efficiencies and mitigate corrosion in those areas. But as you go higher up in temperature, CUI becomes less of a concern. Once you get past 400 degrees, you don't have enough oxygen in that water. Even though there's water there, it doesn't stay long because it gets evaporated. So your CUI concern is not necessarily major at temperatures above 340, but it's major between 120 and 340. That's where you see most of your CUI issues under those conditions. So I want to talk now about the next generation of acrylic TICs, which is our technology that we're working on. So this cartoon gives you a picture of where we are. So the very top section describes our technology. So we have a base coat that we apply at 350 to 400 degrees, 350 to 400 mils thick in one application. We can do 2 if necessary, and a top coat of 150 to 200 mils. Now, I say that, but I also say that you don't necessarily have to apply this film thickness. It depends on your temperature you're operating at. You can go lower, you can go higher. Depends on what you're operating at and what you want to have for thermal efficiency. So we do a very complicated calculation to determine what that film thickness is that gives you that thermal efficiency you're looking for. It's called a NAMR software. And we have some industry experts on our team who are very versed in doing this. A guy by the name of Neil Wiles. The bottom shows the current TIC in the marketplace. As I mentioned earlier, 50 mils per coat. To get to this thickness, you have to apply 8 coats of paint to do that at 18 hours between coats. So in the product development where we are now, we have a one-case system, one component system. It's closed cell, low density material. We can apply to 400 mils, and it addresses CUI concern. And the key here is that because we have intimate contact with the metal substrate, we do a primer, of course, a metal substrate. There's a seal between the steel and the insulation material. When you have mineral wool, there's an air gap between that primer surface and the insulation. That air gap, you have water in that air gap, you have salts in that air gap, they penetrate the coating, percolate through the coating, the primer coat into the metal, causes CUI. In this application, there's no air gap, so you eliminate CUI because the conditions for CUI doesn't exist if you don't have that air gap. So this is a photograph of what it looks like. That's a SCM image. So you see there's quite a bit of pores in that material, giving us a lower thermal conductivity of 0.06 to 0.07. And again, lower the number, better insulation efficiency. Lower the number, better insulation, thinner the coating. So a lot of the coatings in the market today are between 0.08 and 0.1 for thermal conductivity. Therefore, they have to apply several coats to get to a good thermal efficiency. Again, this is an application that we did at one of our industry partners, showing the base coat applied at 300 mils, 24 hours between coats, 3-day walk-on time between the 3-day walk-on time, which is typical, 3 to 4-day walk-on time. Material is 80% solid, so you're not getting a lot of shrinkage. Shrinking is reasonable, but not too much, so you don't have a lot of stress in the coating that causes it to crack and flake and so on. So the top coat is similar. It's based on the same resin technology. Developed with, the top coat was developed to give you a better, smoother surface after you apply the base coat. And the reason for that is that our industry partners would prefer to have a smooth surface compared to a somewhat rougher surface. If you guys are familiar with the ICRI standards, the top coat is probably a 2. Base coat is around 4, 5. So hence the need for a top coat. Well, the top coat could be used as a PPE protection for places where you want to have safe touch. It's used for that. The top coat is also used for solar radiant heat gain. We're doing some testing now to determine, to validate some of the claims we're going to be making on solar heat gain for this coating. So the application development. Application took a lot of time to perfect. We spent a lot of time, a lot of resources in perfecting the application. And so far, we've applied about 13,000 gallons of the base coat and 5,000 gallons of top coat in the field. This is not normal for us. We're a large paint company. And for the smaller ones, this is not normal. So we put a lot of value in getting feedback from our industry partners to understand how the coating is applied, what performance we expect of the coating, and to get a first-hand feel before we launch the product, how the product will fare in the marketplace. So in the center, you'll see the equipment that we use. There are things that are important for us to get the right application. There's a hose length, there's a pump strength, the tip size, temperature, humidity, substrate temperature, and these is what help us to get good thermal conductivity, good sag or hang, good coverage rate, good pore structure. As I showed earlier, we have some pores in the coating that helps us to get a thermal conductivity. On the extreme right, you have a gradation of surface roughness. The bottom is rough and may not be acceptable. So we had to find a way to adjust the pump, adjust all of these inputs to get something that looks like in this range here. So this is not desirable. This is desirable. This is optimum. So we did some recent applications in the USA showing some of the things that I showed earlier here. So some of that, we use some of this learnings to go on a job with our industry partner to do an application. And this is what the surfaces would look like when the coating is applied. And these areas are not, this is just the base coat. These areas are not top coated. So the applications learnings that we spend quite a bit of time doing applications and demonstrations and deployments at a few of our industry partners. And this photograph shows a finished surface with a base coat. And to the right, what you're seeing there is the equipment or just a portion of or an application in progress. So it's a pretty straightforward application, but the work that went into doing it was pretty intense. Future work, we are looking to improve on this technology, even though we think it's very robust, and we're trying to improve the ease of application. We're also working on having a better flow leveling of the coating to give us a smoother surface, and looking at various application apparatus. We're also looking to have even lower thermal conductivity. Today we're at 0.06 on the base coat and 0.07, 0.08 on the top coat. we want to go even lower because some applications require us to have higher thermal efficiencies. And then we're looking at higher temperatures. Could we exceed 350 degrees F in the applications? Additionally, to the right, you see the equipment that we use to measure thermal conductivity. It's, so we have the equipment in our lab to measure these, to do the development. A lot of times, these equipment are not necessarily available to companies who are working in this technology, but we determined that it's important to us, so we purposely went out and bought the equipment to do all the work ourselves in our lab. That makes us go faster, that gets us better understanding of the technology. So in conclusion, I just want to state that it's imperative to have good sealing and adhesion to the surface to eliminate CUI. We can't assume that insulation that's conventional today is completely dry. We prove that it isn't. And ingress of water is critical to causing insulation problems as well as causing CUI problems. So we've developed a thermal insulation system that can be applied at thick films and also provide CUI protection. Material has low thermal conductivity and a reduced carbon footprint. And the reason is because we have lower heat loss versus conventional insulation systems. Reduce carbon dioxide emissions and reduce waste. So this is the team that worked on the project. We had several people from various backgrounds, various inputs to help us to get to where we are today. This product is near commercialization. We're still doing demos at the moment with some of our industry partners and some additional applications with some of our owners and contractors. So that's the end of my presentation. Any questions? And thank you for listening.
Great. Thank you.
Thank you.
Now, when this is applied, and this is a question, once it's on the steel, because it's got that adhesion to the surface itself, it's completely taken out of the CUI protocol in a facility, is my understanding. You may not have gotten into that part, but do you guys know if that would be taken out of your CUI inspections if you had no actual jacketing and it was a coating in place?
Good question.
Yeah, I know we had worked on that with Ineos on a previous version of this a couple of years ago, and they were able to take it out of their CUI inspection completely. So that's why I was curious, because it made a big deal for them at that one particular facility.
Yeah, I can tell you our industry partner we're working with would not be doing that inspection with all the equipment that I mentioned earlier, with the neutron backscatter and so on. They would not be. They're doing visual inspection. Right. Because you can see, now you can see where you have the corrosion. Formerly, with systems you have today, you can't. You have to remove a lot of the surface, the cladding to get to the substrate to see where your corrosion is. But now you can see, because wherever you have corrosion, you can find the exact spot where it is.
Yeah, and I think taking more out of that CUI inspection protocol has an effect on insurance and everything else in our facility.
Yes, and it also, I think the cost of inspection and maintenance is pretty expensive. Speaking to our industry partners, it's very, very pricey to have a maintenance program for conventional CUI insulation materials.
Well, if you were to do CUI with the coating, you'd have to actually scrape the coating off somehow and look at the steel, right? And then recoat it.
No, because this acts as a coating itself. So it basically is a coating rather than an insulation.
So you don't, it's impossible.
Correct.
CUI doesn't make sense.
CUI doesn't exist anymore.
Yeah.
Correct.
Yeah.
CUI is corrosion under the insulation, but once you have that coating on there, unless the coating is destroyed.
Yeah, if you got, if it got physically damaged, you would see the corrosion because it would open up.
All right, so then it does eliminate.
Correct.
Correct, yeah.
Yeah, that's
Yeah.
I just don't know how it works with insurance and all
Yeah,
that.
I mean, to me, not that I know anything about it, but it's the first time I heard, but I mean, to me, it makes sense that you don't have to inspect under the insulation if you put this on,
Correct.
Yeah.
because you can't.
The application method is similar to applying other coatings, or is it specialty equipment?
It's specialty equipment.
It is?
So the gun design was important to get the application,
Right.
to get it to hang at that high fin build. So that's where, but we are looking at different means to apply it as well. So it can be applied by spray application as well as trowel.
Okay.
Some people would do the application with the base coat, then come back and back roll over that to get a smoother surface. So they don't need for a top coat then. But
You blast it first, you blast the pipe further.
yeah, so all the applications we've done so far has been refurbishing of existing assets, where they blast the tank or the tank roof, then they put a primer on there, but it doesn't have to be a CUI primer. I know NACE has a list of different primers that they recommend. You don't have to have that primer. You want to have something that has a barrier, right? But not necessarily a CUI type coating. So any epoxy would probably work. Yeah.
All right, well, thank you very much.
Thank you.
Thanks, Selwyn.
Appreciate
Thank you.
it, guys.